Recording is rolling. It is Monday, September 15th. We're starting the next unit by AP's book. It's unit 2, so dynamics. Kind of all these topics here. A lot of you guys just turned in your kinematic motion quiz to the grade train. So you guys took that home over the weekend. You guys turned in. I will look at those graded today. All right, so here's some of the main topics that you'll see in this session. All right, so we look at Newton's laws of motion. We're properly bringing in forces, which is just a push or pull. So if you push or pull on something, for how much force, which is also a vector quantity, has a direction associated. We'll set up what's called free body diagrams, which are just labeling basically all the forces on an object. Right, a little bit more to it than that, but we'll look at springs and Hooke's law. Like if I stretch on a spring, how much does that spring stretch? Like in terms of like centimeters. Probably depends how much force I put on it. If I put on double the force, I think it stretches twice as far. That would be called Hooke's law. We'll be looking at inclines or classic setups. So what if you have something like sliding down an incline? Like that. Looking at see, I don't have a pulley within reach, but a couple of weight, put them over a pulley. Probably up the street. Well, you guys see a picture later. Okay. And friction force. So it looks like a drag force, like an opposing force. That pushes way, I think friction's opposing that. Okay. See, I printed out you guys out another one of these. I know I gave you guys one very first day of school, but I want to have you guys mark on this one so that it organizes these formulas a little bit better. Because so far we've only gone over three, at least three. And we've got the rest of these to go. Right, so you'll have two of these. You'll have the original one, which will be blank, which will look like the one they give you on test day, and then you'll have this one. Well, we're about to mark this one up. All right. All right. Want to go over posters that we're reviewing with guys, basically all these topics, what to look for. And I do have some Polygon demos, but we'll see if we have time for that. All right, so let's look on here. Let's make a map of what formulas go to what. Right. Yeah, we've only done 3 formulas so far. And it's these first 3 right here. These are these classic kinematic formulas. All right, so okay, you guys should have colored pencils within reach. Now, I don't know if you guys have the same colors I do because I only had so many to go around. So, okay. But there should be about like 4 per desk pod, so you guys can share them around. Okay. So these right here, right, however you want to mark them. Okay. Maybe I'll call those kinematic motion. Okay. There are 3 classic kinematic formulas, which this I always have this available. I found out over the past few years just to have an extra one of these printed out behind me on the board. Of course, I write them a little bit differently than AP does. Like I call X displacement. They call X position. We've gone over this before. They say final position equals initial position plus blah, 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 blah. Right? As opposed to displacement, like a difference of location. Okay. All right. So what are we going into now? All right. So here. I'm going to use colors that match my poster banner colors. Again, I only had so many colors to go around. Okay. Now, this next formula here is a center mass formula. It says the X location of the center mass is the sum of mass times locations, all divided by the sum of masses. That would give you an average location. That's called center mass. Now, that would be along the x-axis. You'd also do y and z axes if you had a 3D object. Okay. I'll categorize that later, so I'm going to skip that one for that. So this one right here is Newton's second law of motion. Newton's second law of motion says, why do things accelerate? So we've been doing acceleration for a few weeks now. I mean, things are accelerating. You throw a ball in the air, 3 balls, comes back down. Right, gravity's pulling down. Acceleration. Okay. But now we're getting to the question of like, why would something accelerate? What would make something accelerate? Because Newton's first law of motion says that, well, if you don't have an external force, then it won't accelerate at all. It'll either stay at rest or it'll just keep moving however it's moving, constant velocity. But this one right here, it says you take the net force, that's the sum of forces, would be net force, divided by the mass of the system or the sum of masses. That tells you how much something accelerates. Okay. Now, skip this next one, I'm going to come back to that. This one right here, friction force. Okay, yeah. So friction force is coefficient of friction times normal force. Tells you how much friction there is. Okay. You guys think if I was sliding this loud lady across the paper, it feels some resistance. Versus across this wood desk, not as much resistance. Versus what if I put down wax paper or sandpaper? Those would have different coefficients of friction. One right beneath it is Hooke's law. And that's one I was telling you had to do with that stretch and spring. Put on 3 times the force, it stretches 3 times as far. That equals kx right here. 3 times the force, 3 times the stretching distance. All right, skip that, come back to that. The A equals b squared over r. Right now, the rest of these are energy formulas and then momentum formulas way down here. Okay, so that'll take us several weeks to get to there. All right. Am I missing any other main forces? Right. So here's where I'm gonna switch colors because we gotta use two more colors today. We have a lot of colors going on. Okay. But by AP's book, Unit 2 Dynamic, but these actually have split into different units, and I think they put way too much in here. So like your next AP classroom, I did open over the weekend. It's there if you want to start reading the questions, but it covers topics that we're not even going to get to until a few weeks from now, so it's not going to be due for a long time. Okay? But so we got some like classic like forces type, right? So we got Newton's second law of motion, we got friction force, we got Hooke's law of spring force. Now, here, oops, might be yellow. This one right here, universal gravitation. You guys see GMM over R squared? Okay, this is Newton's universal gravitation. So, again, it used to be a separate section, right? But I'll put it here, right? And so, how much does the Earth attract you to it, or you attracted to the Earth? Well, if you take your mass and the Earth's mass and multiply together, divide by the distance squared, and this G is called universal gravity for the that'll be like a universal gravity for how much does the Earth pull on the Moon? It's the same expression. Okay. Now, I'm also going to throw circular motion into this. Reason being, because if you have a gravitational force, couldn't you use that to maybe set up orbits? Do you think orbits? And orbits, that's moving like a circular type motion, isn't it? Right. Which you haven't so much talked about yet. Okay. The guys see is A sub C. Okay. Take a guess. What do you think A sub C stands for? Sorry. Yeah, centripetal acceleration. Yeah, centripetal acceleration. It's a type of acceleration, but it's not speeding up or slowing down. It's actually what's the acceleration involved with turning around a corner, right? Which has a similar type of effect, right? Like, if you slam on the gas pedal or the brake in a car, you can definitely feel that. You feel some acceleration, right? You also feel if you turn the steering wheel. And this is the steering wheel equation right here. It's just how fast you're going, the V squared divided by radius of curvature. Okay? So normally, well, okay, I teach that alongside gravity. I've been doing that for not all the time in the future, but the last couple of years. No, centripetal acceleration. Right. Right. Centripetal. Yeah. Right. Okay. Again, energy we won't get to for a while. Momentum we won't get to for a while. But I'm gonna throw in some more here. Let's do right. So while I'm at it, what helps? Okay. You guys are probably going to see one of these turntables again, not maybe in the next 2 or 3 weeks, but maybe about 4 weeks from now or so. Okay. And what if I put a weight on here and we're trying to analyze what's the motion of this weight? What are the forces on this little odd weight right here as this turntable is rotating? What if it has to do with maybe something to do with how far it is from the center? Like what if I have this weight, slab weight versus slab weight, right? Okay. And they're different distances from the center. Maybe a little bit different type motion, right? Okay, so maybe something to do with that. Okay. What am I getting here? So I'm going to switch over to purple for a rotational kinematic. And do you guys see these top three on the right side? Do you guys see how they look the exact same format as these three red kinematic formulas that I've done so far? Right? Because they are the same, except they apply to a rotational system. So these are like turntable kinematic. Right, so turntable kinematics right here. Okay. Now, right beneath that is linear speed, how it relates to angular speed, and the same thing for acceleration. Right, so these two here. And then if you skip way down for some reason, way like halfway down the page is the displacement equivalent. This really belongs with these two up here. I don't know why they split it, put it way down here. Okay. Yeah. So it's like, yeah, that's what's going on right there. Right there. Okay. All right, so while you guys are copying what I got copied, right, everything in orange is like classic dynamics, like just forces. Let's call this dynamics. Okay. Right. This yellow one here is centripetal acceleration. So sometimes I call it circular motion. Okay. Right, centripetal or circular. Okay. This yellow one is gravitation. Okay. And then all these purple ones is like turntable physics. So I'll call that rotational kinematic. What's the yellow? Okay. Yellow's okay. Yeah, so All right, so I got one yellow here is universal gravitation, and this other yellow one is like centrifugal acceleration. Okay? And whenever you have orbits going on, then you have both of those happening sort of at the same time. And so you might have to treat those in combination with each other.
The top ranges.
Rotational kinematic. Okay. So remember, I just broke out that turntable spinning, right? So it's rotational. Okay. And these are kinematic. Okay. And these other ones that is circled down here also apply to the turntable. They relate what's called angular motion, that rotational type motions, back to linear. Like if you point a radar gun at something that says how fast it's going, that's a linear concept, sometimes called tangential velocity. And so yeah, we're starting to build a roadmap here. Okay. While we're at it, let's see. As the semester goes on, maybe I'll have you guys break this out and add more to this. Okay? But these right here are all rotational dynamics. We won't get to these until probably January, maybe at the earliest, maybe January, February. Yeah, here there's oscillating motion. Okay, so pendulums and blocks on springs. Okay, and way at the very bottom, so these last set right here are fluid dynamics, which AP just added to the test last year. Last year was the first year they actually asked questions about like water flowing through a pipe. And these are all related to like water flowing through a pipe or sitting in a tank sometimes. Right.
How does that work?
Huh? How does what work?
What is fluid?
Fluid dynamics. It's like water flowing through a pipe. Okay. So the key is pressure. Like what's the pressure? Like the deeper the water, the more the pressure. But the faster it's flowing, actually, the less the pressure. That's Bernoulli's, which is the very last one. Yeah. All right. So there's we're getting the roadmap going. All right. So you guys good with the roadmap so far? Yeah. What's that?
I can't read the word that's next to the third one.
This one?
Yeah.
It says rotational kinematic. Rotational kinematic.
Bless you. Because he told. Yeah, we're the one who made it. One's bad.
All right, so you guys ready to move on to posters? Posters.
I mean, this is obvious.
So here, do the PowerPoint versions. Now, you guys know you can download this, but you guys know before you ever step foot in this room, this file was already uploaded to Google Classroom, right? So you can download it. Okay. All right, so what variables and units are we talking about? So now, guys, this letter M is used all over the place in physics in different contexts. Like for the past few weeks, has an M stood for a unit of meters, right? But as a variable, not as a unit, but as a variable, it stands for what? Mass. And mass is measured in what? Right, kilograms in this class, right? Now, if you're working with like little tiny labs, sometimes you can do grams and everything's proportionally the same. All the equations are the same, right? But when you're building units, like here, capital F could be generically some kind of force, which is just a push or a pull. That's gonna be quantified in newtons. But 1 Newton, here, let me go to the next slide. Boink. Right. This is one Newton the force breaks down to. Like, how do you measure force? Right. Newtons, right? Guys, is your weight a type of force if you're standing on a bathroom scale, right? So some number of pounds or something, right? Well, in the metric system, we'll call units of newtons. That breaks down into 1 kilogram meter per second squared, which makes sense in terms of like a Newton's second law of motion, right? Is well that'll show up pretty soon, right? But like if you put some unit of force on some mass that could be in kilograms, it's going to cause it to, ooh, guys, meters per second squared. That's a unit of what? Acceleration. Aha. Guys, so you guys just told me something that took people thousands and thousands of years to figure out, which is that if you put a force, if you have a net force on some mass, it's going to cause it to accelerate. That's Newton's second law of motion. Okay. Right. So go back here. So there's different kind of forces. If you see m times g, that's mass times gravity field. Isn't gravity field a type of acceleration? Right. So a lot of times I'll use that to designate weight. You know what else I should put here is F sub g. I should just put F sub g or m times g, right? Because you see F sub g, force due to gravity. Right? That can be measured. Maybe I'll go edit this one. Right. If you see F sub n, that doesn't stand for net force. It stands for something called normal force. Normal means perpendicular. Because if two lines are perpendicular to each other, isn't the math term for that? They're normal, perpendicular, the synonyms, right? So if you have an object sitting on a surface and you like incline that surface to some angle, that surface force that's holding it up from the surface, well, it's always perpendicular to the surface. Okay, right. And then see if an object is sliding across the surface, what's the resistive force? We'll call it friction. So F sub FR, friction force. Right? Notice these are all quantified in newtons, right? They are all different kind of forces. Forces are newtons. Right? Now, speaking of friction, though, like how much friction is there across two surfaces? Like if you slide a weight across the surface, is it your desk surface? Is it paper? Is it sandpaper? Is it wax paper? Right? Wouldn't those all be? Those would all feel different, wouldn't they? They have different resistive forces. And something called coefficient of friction could tell you it's sort of like how much friction there you should expect between two types of surfaces. Guys, what about between your car tires and the asphalt road? Ooh, right, what if it's a dry road? What if it's a wet road? Do you think that would be different? What if it's an icy road? Ooh, right. Right. There's also okay, so static versus kinetic friction. So, um, what if your car is parked and you start to push your car and the brakes are locked, right? Uh, isn't it really hard to break the initial friction to get the locked wheels sliding against the asphalt road? It's really hard to move the car, isn't it? Right? Uh, yeah, maybe it's a little smart car. Maybe you could start pushing it around. Okay? But it turns out once you break that initial friction and it starts sliding, it's actually not as difficult to keep it in motion. Right? The friction actually drops. Right? So that's the difference between a static friction and its coefficient, kinetic friction. Right? Little subscripts that are different. So a little bit different scenarios. So keep that in the back of your mind. That'll probably come up at some point. Oh, this guy here. Tension force. Usually I do S sub T for tension force. Sometimes you see it as capital T. Um, capital T can also be used for time period, so careful about that. Right, and then K, spring constant. Like how stiff is the spring? Because what if you have a really loose spring versus a stiff spring? You guys have been using some spring scales. They're color coded. So actually here, let me switch my screen over and show you. I got some different ones. Okay. I do have two within reach. So like this brown one can quantify up to 10 newtons. Okay, so pulling force. Okay, so it's not too hard to stretch it to 10 newtons. But this one goes up to 20 newtons. So if I put on the same force, it only stretches halfway to 10 newtons. Oh, just like this. But if I put on double the force, I get it to 20 newtons. But that was a pretty similar distance. Right? So do you think this spring is twice as stiff as this spring? Yeah. I might have you do that activity someday to quantify what are all the springs and all the different spring scales. Again, I have two of them there. Okay, so that's how you can quantify this. It'd be a Newton per meter. So like what's the force per unit distance that we pull? We think that way. Okay. All right. Okay, so 1 Newton breaks down 1 kilogram meter per second squared. Okay. Here's another one that didn't make last page is pressure. This might show up a few times. Hold on. Okay, so pressure is force per unit area, or I should ask you guys, but you can see it from the unit. You guys see that, like newtons per square meter? So if you have a big old foam board and you put a weight on it, couldn't that be some force acting on some area like that? Okay. Guys, are you sitting in an atmospheric pressure right now? Atmospheric pressure? Okay. Here, let me throw an idea at you guys. Okay, guys, this can be crazy. You guys want to see something crazy? You're definitely not in the vacuum of space, right? Okay. So this 100-gram lab mass, this weighs 0.98 newtons. 0.98 newtons. Is that basically 1 newton? And it basically calls 1 newton, right? So 1 newton. And 1 square meter, guys, look at the floor tiles. Can you count 3 by 3? Like 9 floor tiles? That's kind of close to square meter. It's a little bit less than 1 square meter. So imagine a big old foam board that's 1 square meter, and I put 1 Newton on 1 square meter foam board. 1 Newton per square meter. Hey, would that be 1 Pascal? 1 Pascal, right? Of pressure, wouldn't it? Right? Now, how many of those pascals are acting on you right now because of the atmosphere?
Yes.
More.
At least
More. 1 million. Oh, not a million. How about 101,000? How about 101,000? Yeah.
What was the question?
Well, if you take it away, you'd be in the vacuum of space, right? Yeah. Guys, we're at the bottom of Earth's atmosphere. Yeah, there's 101,000 of those pascals acting on you right now. Yeah. Guys, another way to quantify that here, I'll switch over to American just for a moment. That's about, I always forget. I think it's like 14.7 pounds per square inch. Right? Guys, 14.7 pounds, is that like an extremely heavy bowling ball?
No.
14.7 pounds? That's a heavy bowling ball, right? Guys, you have one of those on every square inch of your skin right now. Yeah, that's the atmosphere. All right. Newton's laws of motion. So, know these 3 laws. So, first law is also called the law of inertia. This is the one that says an object at rest will remain at rest. An object in motion will maintain its velocity unless an external force acts on that object. So, if there is an external force, then the object will accelerate. That's to say, it will change its motion somehow. It'll speed up, slow down, or somewhere, or change direction. You could also go around a curve. That's also force and acceleration. Okay. I got a real short Paul Hewitt on this. Let me find my. Let's find the old Paul Hewitt here. Paul Hewitt.
And what do we have down here, gang? We have some plates, no staples, no Velcro, the tablecloth. This is what I want you to do over the weekend when you get invited to dinner at someone else's house, okay? What you do is they say, hey, what are you learning at the university? Say, I'll tell you what I've been learning at the university, okay? And get the table all set. Grab the tablecloth like this and say, do you believe in the first law of inertia? And they say, yes, we do. Hey, how about that?
Yeah, so all those objects would want to sit right there because they have inertia, right? So they'll just want to sit right there because of inertia. Right? Paul Hewitt has some other first law examples, demos. You guys know I uploaded all the Paul Hewitts in some zip folders on the very first week of school, right? So they're all there. You can watch them all. Right? Newton's second law. Acceleration of an object is directly proportional to the net force acting on it and inversely proportional to its mass. Right? And so here's the fraction form on the left, and here's a common way to write the non-fraction form on the right. Okay, so how much does something accelerate? Because you guys have been working with acceleration for a few weeks now. You say, okay, something falling in Earth's gravity, it'll accelerate up to maybe 9.8 meters per second squared. Right? Okay. Now we're saying where acceleration comes from, how you get it. Okay. It comes from a net force acting on a mass. Right? Maybe this is why if objects are in free fall, right, like a heavy object weighs more than a light object, so it has more force on it. But it also has more mass. In fact, since those are directly proportional, they'll accelerate the same. That's the classic physics one explanation of that. Okay. Or sometimes you see it this way: net force results in mass times acceleration. Okay. Now, I usually prefer the fraction form if I can, right, because I think it shows cause and effect a little better. Like, why do things accelerate? Because there's a net force acting on a mass. Anyways, when I say net force, do you think there could be like 10 different forces acting on an object? And first you could find as if it was a single force, right? So here, I'll draw this out just to make it really, really clear. Okay. What I mean by net force. Okay. Net force is as if it's a single force. So if you got some object here, okay, like some object, there's my object, right? Okay. And what if I'm pushing up and to the right at the same time? So I'm pushing. Okay. So and as a rule, so we get to diagrams. You always have the center mass dot and draw the forces extending away from it. So if I'm pushing up, cause the force up. Okay. And I'm also pushing to the right. Let's say I'm only pushing to the right a little bit. Call it force to the right. Okay, put the right a little bit. Okay. And so I'm pushing up a lot and to the right a little bit. Do you think this is going to go up a lot and to the right a little bit? Maybe kind of off on that angle that way. Great, like that. Great. So maybe this is like 30 newtons and this is only 10 newtons, something like that. So overall. So what I can do is I can connect these vectors tip to tail, like slide this one up here, and then create a resultant force. And this resultant would be the net force, call it F sub net, which is different than F sub normal. I know they both start with the letter N. That's a different thing. So F sub net, the net force, it's as if it was a single force acting. Okay? If you guys identify what is a single force and what is the mass, you can divide those two to get the acceleration. Right. Now, what I did not draw in there, maybe I should have drawn a friction force too. That could be resisting all that motion, couldn't it? Right. Right. Okay, Newton's third law. Ooh. Okay, so this is the equal and opposite rule. Right. So for every active force by object A on object B, there's a reactive force equal in magnitude, opposite direction by object B, back on object A. So whenever you have two objects interacting, they're either pushing on each other or they're pulling on each other. Because that's what a force is, right? It's just a push or a pull. So you could strip it down like one dimension, right? So maybe this cannon versus this cannonball. Okay? As this cannon blasts this cannonball, is there a force on the cannonball? Yeah, to the right. Is there a force back on the cannon to the left? Yeah. Okay. But guys, which force is bigger? They're the same. They're the same. That's what the word equal means. Oh yeah, I trip up everybody every year with that. I can't wait. Yeah, yeah. How about this, guys? Is the Earth pulling on the moon?
Yes.
Yeah, that's what's keeping it in orbit, right? Hey, is the moon pulling on the Earth? Yeah, okay. It's why we got tides and stuff, right? Right. Okay, but which force is bigger? Equal, the same. Yeah, the same force, Right? Now, even though these are the same force, they don't have the same effect on both the object. That's why this one isn't super intuitive the first time you see it. Right? Because guys, which accelerates more, the cannonball or the cannon? The cannonball, or yeah, the apple, I guess, right? Because I'm making some apple cider here. So yeah, now why is that? Well, I have to go back to Newton's second law. Now it's the same force on the cannon and the cannonball, or the same magnitude force, opposite directions, of course, okay? Acting on completely different masses, right? Different masses, same force on different masses results in different accelerations. You see that? Right? And then how about the Earth and the Moon? Same force, right? But which is way more massive? The Earth. If I go back here, if it's more massive, does it have more or less acceleration? A lot less, and then vice versa for the Moon. Right? And of course, this time we're talking about like a centrifugal type acceleration because it's in orbit. It's just changing direction, isn't it? Okay. Actually, here I have a really good. There's a plug here I really want to show you guys on free fall explained, but it's like 5 minutes long. But I have a different one that kind of encapsulates both the third and second law altogether.
And you fire a rifle. Here's the bullet. Bullet races out. And the bullet has a force acting. But that gun kicks back. How much force? Really the same? The same. The same force acting back. Now, the acceleration of a bullet, a lot or a little? The answer begins with an L. A lot. Because here's the mass of the bullet. Here's the mass of the rifle. So here's the acceleration of the bullet.
You see, right? He's right in the middle of explaining Newton's second law, actually, isn't he? Right? He started out Newton's third law. Right? It's the same force, opposite direction. Because inside the gun barrel, there's just some explosion that's just pushing everywhere, all different directions equal. Right? It's just pow. Right? So equal force on the bullet and the rifle. Right? But now he's kicking back over to Newton's second law to explain how it changes the motion of these things.
But here's the acceleration. So the rifle only goes back to here. In the same time, the bullet goes from here to here. That bullet is accelerating like bonkers, right? Inside the barrel. Now, when it gets outside, is it still accelerating? No. Now it coasts. We talked about this before. It's accelerating down. Why it drops. It follows the curved path. But while it's inside, the forces are the same, but the masses are different. That means that the effects are going to be different.
Okay, we go. All right, so you guys go with Newton's laws? Newton's laws? So know those. All right. Here's a, okay. Do you guys know a YouTube channel called Veritasium? Maybe? Okay, so one is very old ones from a long time ago. I stole this from him. So, because Newton's third law, this is one that, yeah, it's easy to hear. Like a few months from now, there'll be some third law question that comes up. I'll say, which force is bigger? And see if I can trick you guys again. Okay? It's not super intuitive, maybe to everybody the first time you hear it. So why is the force the same between the Earth and the Moon? Why do they pull on each other equally? Right. Well, what if you broke them down to like, just sake of argument, what if you had 3 times the mass? Like this planet's 3 times the mass of its moon. Okay? Well, if you just isolated mass and mass, like, okay, if it were equal masses, they would definitely pull each other the same. Right? But then these 2 equal masses also pull each other the same. And these 2 masses also pull each other the same. So you see the net effect. Like if this is 10 newtons force and 10 newtons to 10 newtons, that conspires to make 30. This is 10, 10, 10. So that's also 30. Right? It's just the opposite direction, right? Right, so equal and opposite, third law. Right, so here's the acceleration bridge. Acceleration bridge. So you guys remember those 3 kinematic formulas you've been using over and over and over last few weeks? So I rearranged them. These are the 3 kinematic formulas here in disguise. They're all set equal to that acceleration, like sort of algebraic rearrange and you solve for acceleration. Okay, so this is how we've been thinking about acceleration for the last few weeks. Here's the new way of thinking about acceleration. It's like, where does it come from? Well, it comes from a net force acting on a mass. So now you have a way to figure out, like, if you see a question, for example, somebody kicks a soccer ball. I tell you the kicking force and I tell you the mass of the soccer ball. And I say, like, how fast does it leave their foot? I have to tell you something else, like maybe how much time were they kicking it for, maybe a fraction of a second, right? But at some point, there's enough information where you say, well, if I know the force acting on the mass, right, I know maybe like how much time it was acting for, maybe it starts from rest. There's enough information where you can navigate this acceleration bridge as a variable, right? And figure out like how fast did it leave it at the final velocity. Okay, we do that. A little room there. Right? All right, how about the bottom half of this? The bottom half is the rotational equivalent. You guys remember I was breaking out the turntable earlier today? Right, you guys circled some formulas and I had them in like a purple colored pencil. Okay, so in an acceleration sense, maybe a turntable could speed up spinning because there's something called a torque acting on it, acting on a rotational inertia. Okay, and then here's the three kinematic formulas as they apply to turntables. Okay, how far is it turned? I think. Okay. Here's Hooke's law for springs. So suppose you got a spring. This middle one, see it's labeled unstretched. Okay. And then what if I put a force on it to stretch it? How much force would that take? Right? What if I compress it? How much force would it take to compress it? And the more I compress it, you guys see this X right here, or the more I stretch it, this X, do you think it takes more and more force? Or vice versa, the more force I put on it, the more it stretches or compresses. Right? And it turns out for something called an ideal spring, that should be a linear relationship. Okay. So if you put on 3 times the force, it stretches 3 times as much. That would be linear, right? Linear relationship, right? The slope of this line is do you guys remember what does K stand for in this context? Spring constant. Spring constant. Yeah, which is how stiff is the spring, basically. Right? Like here, guys, if you had a really, really stiff spring, would it be true that it would take lots and lots of force to stretch it just a little bit, and this would be a really steep line, and K would be huge? What if it was a really like loose, like a slinky, like a slinky spring? Do you think a little tiny force could stretch it a lot, really easy? And then what would that look like on this graph? Yeah, really shallow slope, right? So maybe like down here, right? And the K would be really, really small, wouldn't it? Okay. Now that green triangle, you guys see that green triangle? U stands for energy. It also takes some work or some energy to stretch or compress a spring. We're not going to talk about that for a few weeks, but eventually we'll come back to that green triangle, just not for a while. Okay. Right. Here's a different version of Hooke's law. Guys, look, the slope reversed. Now it's a negative slope. You guys see it? Negative slope. Right. So this is what's called a restoring force. Actually, a lot of textbooks just jump straight to this. They just teach it this way instead. They say, well, if you compress the spring is actually pushing back in the opposite direction. Hence, the whole thing is negative. Okay. Or if you stretch a spring, the spring pulls back the opposite way that you're pulling. So this is the restoring force. You guys see that? Okay. So be ready for Hooke's law in like either one of these. Right? Depends just how you define what force are you talking about. Are you talking about the applied force? Or are you talking about the restoring force? Okay. Right. Right. So I might have you guys do a loud what's the spring constant of all these different springs? I got a red one and a brown one over here, but there's other ones too. Right. All right, free body diagrams. And so these are a big deal. This is a diagram that labels all the forces. Okay, and moments acting on an object. A moment could just be a torque, so it's like the turning version. Okay. Sometimes these are called force diagrams. If you just label the forces. Okay. So normally I'm just talking about forces. Okay. Now, really important aspect of this. Sometimes you have objects in motion, like maybe like this object might be falling free fall, or maybe this block might be sliding down the incline. Maybe I don't know, or maybe you're pulling this block across the surface. It might be in motion. But you guys see this note at the bottom? Right? It says velocity vectors are not part of free body diagrams. Right? Now, a lot of times what I'll do if I'm trying to show something in motion, well, AP's version might be to draw these little streak lines. You guys see those little streak lines? And say, okay, well that indicates this motion. Normally, I draw like a 2D fat arrow to distinguish it from all these other proper force vectors. Right? You see how all these proper force vectors are connected to a center mass dot? Right? So like this object can free fall off the edge of a cliff. Right? Draw a center mass dot and then a weight, and maybe that's it. If there's no drag force, that would be the entire story. Right? Or this block on an incline, it can have 3 forces. I got its weight pulling straight down towards the center of the earth. Okay? Do you guys remember what this blue one's called? Starts with an N. Normal force. See how it's perpendicular to the surface? Perpendicular? I'm going to have you guys draw some of those. Can you guys draw a line that's perpendicular to the surface? Okay. And then friction always opposes motion. So yeah, it looks like this block would be probably sliding down or trying to slide down the incline. And friction would be opposing that. Right? You see how friction would be parallel to the surface? Okay. And here's dragging a block across the surface. Right? You get all these different forces popping up. Okay. All right. So let's go through some of these. I might quiz you guys maybe tomorrow. I don't know. We'll see how this paces out. But what if you have a rocket in deep space at constant velocity, just zooming through space, super fast? Okay? You guys, what would it feel like inside that rocket? Remember, the engines aren't on. It's just coasting. So could that be like the International Space Station, just as it's in orbit around the Earth? Right? And what does it look like inside the International Space Station? Are they just floating around? Like as if they're in deep space. So there are no actual forces. So you wouldn't actually label any forces. So the correct answer would be to just do nothing to it. Okay, something like that. How about what if there's an air hockey puck that's going across an air hockey table? So yeah, do this fat velocity vector to indicate that it's in motion, but that's not actually part of the diagram. And if AP asked you to draw something like the free body diagram, you wouldn't actually all that, right? They wouldn't be looking for it. Right? What they would care about are these two force vectors that I have connected to the center mass dot. So this object has a weight. That's what mg is, right? Mass times gravity field has a weight. It's pulling straight down. Okay. And then do you think the air jets are holding it up with an equal and opposite force? Because it would be in equilibrium. Okay? Now, equilibrium means there's no net force, which might possibly be at rest or might be at constant velocity. But you guys know that those are basically physically indistinguishable. Like if, like from the frame of reference of, like, what if you were an ant crawling around on the air hockey puck? Right. So I'm ignoring any kind of air drag. So that aside, whether you're at rest or if you're constant velocity, if you have your ant eyes closed, you cannot distinguish the difference. You cannot feel the difference between being at rest versus constant velocity. Okay. Right. And that free body diagram, yeah, that might be an air hockey puck at rest. If they get rid of this green velocity over here, it might be at rest. It would be the exact same free body diagram because it's the same two forces. Okay, same two forces. Okay. Now, what about this? What if you hit the air hockey puck with a paddle? How? When you hit it with a paddle, would that be a third force? Yeah, right. Which is not what's being shown up here. So if I'm hitting it with a paddle, I would have to include that force, and that actually would get it going to start with. Okay, that would be a third force. All right. What if you? Yeah.
About the air hockey puck holding.
Huh?
Because my cousins have a table. Whenever I turn it on, the puck goes from not moving to just randomly moving.
Oh, kind of drifts around a little bit. Yeah, okay. Yeah, there might be like tiny little forces. Like maybe one jet pushes a little bit more than another, so it kind of drifts around a little bit. Yeah, but basically doesn't. It's not like if it was accelerating, like takes off and like accelerates like towards the goal, that would be like, okay, there's something weird going on. All right. But yeah, you guys know in this class a lot of times we'll like simplify things, approximate things. Like ignoring air drag is common, ignoring friction is common, right? Rounding gravity a little bit. Yeah. So approximations. Tell you basically how things work. Okay. Pulley block at constant velocity. This can be part of a lab setup, but here's all the forces going on with it. So maybe there's an applied force, or you could say spring force if attached to a spring scale. Maybe you're pulling it to the right. Okay. Maybe I got the weight down, pulling it straight down, and there's a normal force from the table holding it up, preventing it from plummeting down to the earth. Okay. Now, guys, look at my diagram. What would you say is the net force according to how I drew this? What's the net force? Zero. See how they all cancel out? See how the vertical ones definitely cancel out? The normal force and the weight cancel out? I mean, that's to be expected. Okay. But the horizontal ones also do in this particular case. It looks like I'm pulling to the right as much as friction is dragging to the left. Right? Guys, if there's zero net force, is this block accelerating? No, because Newton's second law of motion says zero net force results in zero acceleration. Is that F equals ma? Yeah. Right. So this block might be at rest. Maybe I'm pulling it really hard, trying to get it to move, but we can't get it to move. In which case I would call it static friction. That might be like this red one. Yeah, FFR is force due to friction. Yeah, friction force. Yeah, FFR, friction force. Right. All right. Or it might be drag. Or if the block is in motion, guys, if the block is in motion, it's moving how? Constant velocity. Yeah. Right. Because guys, constant velocity would also be zero acceleration, wouldn't it? Okay. So something can have zero net force and it can be in motion. It would just be constant velocity, which means straight line at constant speed. That could also be the case, right? And that would be more like applicable to this green one here. Okay. Now the formulas look similar, except something about this coefficient of friction, right? Kinetic versus static friction. Okay. Here's some common values. Now, coefficient of friction is a material property. And again, there's two of them. There's a kinetic one and there's a static one. Okay? So wood versus wood. Now there's different kind of wood. So this is kind of a round ballpark number, but generally speaking, so coefficient of friction of 0.5. What that means is if you go over here, friction force compared to normal force, right? To sort of get an object moving. Let's say you're pulling with the spring and you want to overcome the friction force. Right? Do you guys see this normal force would be equivalent to the weight for this very basic case if it's just a flat surface, right? So you can kind of substitute that in too. So basically kind of cut to a solution here. Right? If this object weighs 10 newtons and it has a coefficient of static friction of 0.5, do you think it takes about 5 newtons of force to break the initial friction and get it start to slide? Right? You guys see that? Because 5 would be half of 10, hence 0.5, right? But to keep it in motion, turns out you actually don't need as much force anymore. Suppose this block weighs 10 newtons. How much force do you think you need approximately to keep it in motion? Yeah, about 3 newtons. You guys see that? Okay. That's all that means. That'd be this one. Also, once it is in motion, you can always make an exact equation. It's just equal to this exact ratio. friction force compared to normal force, which is like these two here, ratio. Okay. But with the static case, you guys notice that it's actually an inequality sign. And I think you can figure out why. Because if you pull with a little force, maybe the block doesn't initially move. You pull with like a medium force, it still doesn't move. Pull a little harder, pull a little harder. Right? You guys see like the force has to build up until finally you can break that initial friction. So that building up process is why it's an inequality. Here. Like that. Here, let's look at some of these. All right, so we got all these different materials. These last three rows I have tires versus a road. Now, icy road, wet asphalt, dry asphalt. Right. Now, dry asphalt would definitely have the most friction. Right? It's easy to get the tires to grip to the road and get the car going. It's also easy to stop it in a hurry. Right? So again, these are kind of round numbers. Like if you have a brand new paved road, maybe like 90%, I could interpret this as right? Versus the 70% if the tires are skidding. But look, if the road's wet, not as much friction. If the road's iced over, hardly any friction at all. Okay.
Why is there such a big difference between the two frictions on glass?
I don't know. Yeah, that's an interesting question. Yeah, why is there such a huge drop off, right? It's really like if you have glass and glass, yeah, it's really hard to break the friction. Once it is broken, yeah, it's not nearly as hard to keep it going. Yeah, that's interesting. I don't know, right? Probably something down at the molecular level, maybe something to do with like the chemical composition, something like that. Right? Also, there's different kind of glass, so yeah, all right, it's that too. Okay, so all right, here's a question I ask every year: is you guys just got your driver's licenses, probably, right? Did you guys have to learn about something called anti-lock braking system? Anti-lock braking? Yes, you did. Okay, I know I did. Okay, anti-lock braking, guys. Here's the physics of anti-lock braking. It's right on the slide. It's these last two right here. 0.7 versus 0.9. So suppose you have a car from the 1970s, and so it has no fancy anti-lock braking. Right? You slam on the brake, and the car, the tire's locked, and doesn't the car skid to a stop? Leaves those skid marks on the road. Okay? You're taking advantage of this coefficient friction right here is 0.7. Right? Now, what they used to recommend, now don't do this today, but if we were back in the 1970s, they used to say don't actually slam the brakes, but actually like pump the brakes, because if you can get the wheels to rotate a little bit so they can get some static traction with road, you can actually take advantage of this larger friction value, this 90% rather than 70%, and the car would actually come to a stop sooner. Right? Now, nowadays, go ahead and slam the brake because your car has the anti-lock braking system. A computer system will take over and it'll automate that process for you. So that anti-lock braking will actually, and that's what the word means, right? Anti-lock, right? It actually rotates the tires a little bit. Right? It helps you maintain static traction with the road, so you can take advantage of this larger friction, and the car will actually stop sooner. All right. All right. Lab table. Here's that. Oh, speaking of car braking to a stop. Okay, so here's a classic one that you guys should know. Is here. Let's go through it. So here's Newton's second law of motion. Net force results in mass times acceleration. Here's a corresponding free body diagram. So it looks like the car was going to the right. The car has a weight pulling down. There's the road that's holding up. This is just a level road. So I think the normal force would be equal to the weight if it's a level road. We'll get to inclines later. Okay? And then you're slamming the brake. And so there's this friction force between the tires and the road that's bringing the car to a stop. That's the entire free body diagram. That's what it looks like for anything slowing to a stop, right? Slowing to a stop. Right? Now you guys did some kinematic curves slowing to a stop, like in terms of motion, but now we're looking in terms of forces. Boom, right? Okay? So how much can the car sort of slow down? What's this acceleration? Well, let's go through this derivation. So this friction force would be the net force, wouldn't it? Don't the two verticals cancel out? And so the friction force is the net force. Do you guys see that? Right? That's what I did right here. In place of net force, I just put friction force because it is the net force. It's as if it's the only force. Right. Okay. Right. Now, if I go back to let's say either one of these. Right? I'm taking advantage of either one of these frictions. Can I cross multiply the normal force and say normal force is coefficient friction times normal force would result in friction force? A little algebra switcheroo, right? That is this line right here. Friction force is coefficient of friction times normal force. Either taking full advantage of the static, or if it is sliding, this would be kinetic friction. So I left that ambiguous or something, right? And that results in mass times acceleration of the car. Now this acceleration maybe is sort of like deceleration. It's like trying to slow down the car. Although maybe you're trying to like speed up and get away in a hurry.
Negative number if you try to slow down.
Yeah, true. Yeah, actually, most textbooks would probably call this negative at this point and have this as negative mu g. I might actually change the slide and put a negative in here. Yeah, that's a good thought too. Because the forwards is positive, acceleration would be negative, wouldn't it? Yeah. Okay. So here I'm just looking at like absolute values sort of. Okay. And then this normal force would be equivalent to the weight. Ooh, guys, what variable cancels out? Cancels out the mass of the car. So what if you have an empty car and you're trying to brake to a stop? Versus you go to Publix and you have a car full of groceries. Like, ooh, it's Thanksgiving time. You go brake to a stop. Guys, which car brakes to a stop sooner? Huh? You guys just told me. The mass cancels out the same. The mass cancels out. Guys, the mass cancels out. That was a really classic physics question. Okay, so empty car, car full of groceries. Yeah, they break. They break the same because they accelerate the same. They slow down the same. Hence, they'll come to stop in the same distance. Right? Okay, so all that matters is what's the coefficient of friction between the tires and the road, and also the gravity field that you're on that tell you how fast the car slows down. Okay. Actually, this one actually here is a military entrance question. So if you go join the military, they'll probably ask you this exact question. Let's say, what are the four forces acting on a plane at constant velocity? You guys, constant velocity. Whenever you see constant velocity, right away, you know the net force is equal to what? Zero net force, right? So all your forces better cancel out. Now you can have different forces, but they just better cancel each other out. Okay? So do you guys think there's a weight pulling down and a lift force, and they basically cancel out? Okay? And maybe the plane engines are thrusting it forward, but there's also, realistically speaking, a drag force at this point that you would have to consider. Right? I'll cancel out. Okay. This is as far as I'm getting today. Yeah, getting near the end, aren't we? Yeah, guys, I'll show you some drag force, which is not going to show up in this class so much, but I think it's good to know anyway. So, like, how does a parachute work? So parachute work. Oh, I got messed up a little bit. Okay, no PowerPoint here. Do you guys think the faster you're falling, the more the drag force builds up? Yeah. So now we're considering something we've been ignoring for a few weeks, okay? Which is this air drag. Now it turns out air drag is proportional to the speed squared. It's also proportional to this cross-sectional area. That's why you want a big parachute. The density of the air and its coefficient of drag. Put it all together. Different coefficients of drag. Boom, boom, boom. Okay. You guys ever heard the term terminal velocity? So last week, V versus T, isn't it just a linear relationship, just straight line, increase speed forever? But if you include air drag, it's going to eventually reach its terminal velocity. So it will eventually go down at constant speed if you also include the air drag, because the air drag force matches the weight force. And at that point, you have terminal velocity. Okay. Which for a parachute, hopefully is pretty slow, right? If you have a parachute, hopefully it's fairly slow. Maybe this line should be like way down here, right? It's terminal velocity. Okay. We'll be doing some inclines. We'll be doing some outwards, but it's gonna take us some time. And okay, that one looks fun right there. All right, you guys have a good day. Well, I think I'm somewhere tomorrow.